So, in the next few last few modules, we talked about basic concepts of quantum mechanics, and we talked about the postulates of quantum mechanics. We talked about how to act with the operators, what is the operator algebra. Then I talked about simple system like particle in a one dimensional box, two dimensional box, three dimensional box. Then we talked about what happens if one of the wall is of an infinite potential well becomes finite, and then we also talked about that what will happen if you have a potential barrier, and that is called quantum mechanical tunneling in the last module. Okay. So, now we will be doing the same thing. We will be doing applying the Schrodinger wave equation to another model system called simple harmonic oscillators. Simple harmonic oscillators, name itself tells you, SHO is a periodic motion. All of you know that if you have a spring attached to a wall and you stretch it by apply a force in this direction, which is called the driving force, and then you leave it, then a restoring force sets in, and this restoring force, if we denote as Fr, this is proportional to the distance to which you stretch it. Okay. It is like a pendulum of a wall clock. If you it is at equilibrium, it is in the middle, and after that if you take it on any one side, or the left side or right side, and then you leave it, a periodic motion sets in. Okay. So, this is it is the same thing which you have done in your 6th, 7th level or 8th level of physics. So, this restoring force is proportional to this one, and if it is so, we can write restoring force becomes equal to minus with a constant k. We say this constant k to be the force constant. K is called force constant. This is what is Hooke's law. Okay. We are talking about Hooke's law, which is part of your high school syllabi, Hooke's law. Okay. Now, we will deal with a motion like this one. Previously what we did, we imagined a model system in which the particle was present on one line moving in one motion, one dimension, and we put infinite boundaries on the two sides, and we restricted the motion at the boundary at x is equal to 0 and x is equal to a. Now, what we are doing, this is also a one dimensional problem, but it is a periodic motion, from left to right, right to left, and the equilibrium position is in the middle. Okay. Now, this we can write as, if we, since force is mass into acceleration, so what you can write is m is equal to d square x by dt square, and then you can write minus k over m into x. Sorry, m you bring on this side, m I have brought this side. Okay. So, this we can write. Now, if I suppose this part k over m, I write it as omega square, then will be written as minus omega square x, where this omega we call is angular frequency, and which has a unit of radian per second. And what is the unit of linear frequency? It is per second. Okay. So, in order to equate these two dimensionally equivalent, it will be when omega becomes equal to 2 pi nu. So, linear frequency and angular frequency is related by this equation. Okay. Now, if you look at this equation, it is very simple to the previous equation which we have done already. It is a double differential equation. So, you need to write a solution for this double differential equation, and that you can do very easily. So, d square x by dt square is equal to minus omega square x. So, the solution will be x at time t is equal to a sin omega t plus b cos omega t. Okay. Now, if I write at time t is equal to 0, okay, this is the time at which you bring the pendulum to the maximum displacement. Okay. So, or you stretch the string to the maximum displacement. So, what you say, displacement is maximum at this time. And what is displacement? Displacement is x. So, x is maxima. I equate it to a prime, and if you put these two values, x is equal to a prime and this one, then at time t is equal to 0, x at time 0 will be, first part a sin omega t will become 0 and then it will be b, and this will be equal to a prime. So, a prime is actually b, and then we say that x at time t we can write as a prime cos omega t, because sin term becomes 0, applying the boundary condition which we are now expert in doing it, because we have done for many of the model system previously. Okay. So, this is your x at time t is equal to a prime cos omega t. If you put this value in the original equation, d square by dt square a prime cos omega t is equal to minus omega square, omega square x. Okay. Then what can we do? We can differentiate this twice, and it will be what? A prime minus omega square cos omega t. Double differentiation, so minus omega square cos omega t minus omega square. Okay. So, this we can do. And what is omega square? Omega is equal to, I have taken as omega is equal to root under k divided by m square. Okay. So, omega square we can write as minus a prime and then omega square a prime, or a prime I should take it this side, minus omega square is equal to a prime cos omega t is equal to minus root under, the minus and minus will go. So, remove the minus sign, minus and minus will go, you will have root under k divided by m for omega square is equal to k divided by m. No, let me do it again. Okay. So, what we know, the original equation of was m into d square x by dt square is equal to k into x minus k into x. If we put this value of x in this equation, then what do you get? You get d square a prime cos omega t divided by dt square, d square by dt square. Okay. And then you get minus kappa into x. Okay. So, this you can write as, if you double differentiate, you will get a negative sign, and this negative sign will go, and you will have a prime omega square A prime cos omega t is equal to k into x. And this A prime cos omega t, this will not be there, okay, it will be m omega square, and A prime cos omega t is equal to x, and this omega square is how much? It is k divided by m. So, we can write as omega square is equal to k divided by m, okay. And then you have this as a cos omega t is equal to x at time t is equal to kx, okay. Or you can write m omega square x into kx. So, x and x will go, and what you will have is omega square is equal to m omega square is equal to k, and k is what? Omega square is equal to k over m. So, k is equal to m omega square, this we have supposed. Now, if you put the value of omega square as 4 pi square nu square is equal to k, then you can write nu square is equal to 1 over 4 pi square this side into k divided by m this side, and so nu will be equal to 1 over 2 pi root under k divided by m. So, this is called linear frequency of simple harmonically oscillating system with mass m, okay, where mass is m and k is mass is m and k is force constant, okay. Now, this is all classical concept of equation simple harmonic oscillator. If you go for energy you can get from the force. So, the energy will be, energy we can write as E is equal to minus Fr restoring force into dx, and since it is a one dimensional problem, so minus infinity to plus infinity. So, this will be equal to, energy will be equal to, Fr is kx minus kx, so it will be minus infinity to plus infinity into k into x dx, and so energy we can write as k x square divided by 2, and k is what? K is m into omega square, so we can write 1 by 2 m omega square x square. This is the potential, this is the energy of the system, okay. So, we have determined the energy, we have calculated the linear frequency, nu is equal to 1 by 2 pi root under k divided by m of the classical harmonic oscillator. We have not done anything quantum, classical harmonic oscillator. Just to refresh your memory of harmonic oscillator, that what is it, okay. Now, when you go for the quantum harmonic oscillator, the potential energy, the energy which you get, vibration energy which you get is V plus half into h nu, okay. And I said you that the relationship between 2 pi nu is equal to omega. So, what you can write is V may be equal to V plus half, in terms of angular frequency it will be h cross into omega, because nu will be omega will be h divided by 2 pi, you can write as h cross, okay. So, this is the potential where this V is called, I have directly written the relationship without going into the derivation, that this is the potential energy, vibrational energy of harmonic oscillator. This you get, this we will derive later on, vibration energy of simple harmonic oscillator, and I will tell you that this V value becomes 0, 1, 2, 3 and so on. Okay. So, for any simple harmonic oscillator, the quantum mechanical harmonic oscillator gives you an energy equal to V plus half h nu or V plus half h cross omega. For a classical harmonic oscillator, the energy which you obtain is 1 by 2 m omega square x square. Okay. So, this or 1 by 2 k x square, whatever you say, both energy 1 by 2 k x square can be energy, or 1 by 2 m omega square x square is the energy. Both are equally valid equations. Okay. So, what will happen? If you look at these two equations and if you put V is equal to 0, the energy becomes equal to V1, it becomes equal to half h nu. Okay. When you put V is equal to 1, it becomes 3 by 2 h nu. If you put V is equal to 2, V3 becomes 5 by 2 h nu. Okay. But if you look at this equation, here you have x as the displacement, here you have x as the displacement. So, if you make displacement 0, x 0, then the energy is 0. So, in contrast to classical harmonic oscillator, quantum harmonic oscillator has never potential energy, never energy 0, potential energy 0. It is always the minimum energy which is possible for V0, and this becomes equal to half h nu, and this will always remain present even if you bring the system to 0 degree Kelvin, and this is called 0 point energy, which is always present. So, see the difference between a classical harmonic oscillator and quantum oscillator. This I am talking about are the results of the quantum mechanical calculations, which we will do very soon. Okay. But this 0 point existence of 0 point energy is in complete contrast to the classical harmonic oscillator. In a classical harmonic oscillator, you can have 0 energy, but in case of quantum harmonic oscillator, the energy is always minimum energy is half h nu or half h cross omega, whatever you write. Okay. Again, in terms of h cross omega, it will be half h cross omega. Now, if you look at this equation 1 by 2 k x square or 1 by 2 m omega square x square, and you plot a graph of energy versus displacement, then what you get is a parabolic potential. Parabolic potential. Okay. And if you make it energy levels, then this is the minimum energy, 0 point energy called half h nu or half h cross omega. Then you go for the second energy level, a third energy level, a fourth energy level, and all the third will be 3 by 2 h nu or 3 by 2 h cross omega. It's half h cross omega, and the difference between the two will be of h omega, h cross omega. The difference between the two will be h cross into omega. The difference between the two will be h cross into omega. Okay. So, equidistant energy levels, quantized energy levels you get in when you apply Schrodinger wave equation to simple harmonic oscillator. Okay. So, the existence of 0 point energy is in complete contrast to the classical harmonic oscillator. In classical harmonic oscillator, you can have a 0 potential energy. Why these are the quantum mechanical results I am discussing, and I am discussing it because when I will start doing the calculations of Schrodinger wave equations, it will be mathematically a little cumbersome. You will have to bear with me, because there are two methods of finding out the solution of Schrodinger wave equations. One is through the ladder operator and another is through the power series method. So, we will talk about both these methods, and it will be a little more mathematically complex, but you will have to bear, because the beauty of the simple harmonic oscillator calculation is in its mathematics. But before I go for those calculations, I want to tell you that what is the important points, important lessons which you will get from this calculations, so that you don't think that why I am doing so much of mathematics and doing so many calculations. Okay. So, I want to tell you that this is 0 point in existence of quantized energy levels. Existence of 0 point energy levels are in contrast to the classical harmonic oscillator, and it should be so, because if in the classical harmonic oscillator you say the position is potential energy could be 0, then when it will be 0, when at x will be 0. So, what you know the position, x is known to you, and if x is known to you, then the uncertainty in position is 0, and if the x is 0, position is static, system is not moving, then momentum will also be 0. So, momentum is also known. So, classical harmonic oscillator, where you say that the position is known, momentum is known, is in complete disagreement with the uncertainty relationship. And when you go for the quantum mechanics equation, quantum mechanical results, you say that the potential energy has some minimum value which is called 0 point energy, half h nu, and so it does not it has quantized energy levels, equidistant energy levels separated from h cross omega. Then we say that the system is not static, it is moving, so you do not know the position and momentum simultaneously. Okay. So, it is in agreement with the Heisenberg uncertainty principle. But why at all we as a chemist are doing this problem? This was a simple harmonic oscillator was a problem of what till now what you have done is simple harmonic motion is in physics syllabi. So, why we are doing it as a chemist? Let us see. We are interested in that if you have two atoms A and B, and they are very widely separated, A and B, then they do not interact. When they come close together, they form a chemical bond, and if you bring them further closer, there will be electronic repulsion, electron clouds will repel. So, if you draw the change in the potential energy in doing this, then initially when they are not interacting, the potential energy will be 0 at some distance x. Okay. But gradually when they come close together, the potential energy decreases, and again when you bring further it closer, the potential energy rises. Okay. And I know you have this, you must have done this earlier also. This distance is the distance of bonding, called equilibrium distance. Okay. So, this is called potential energy surface of diatomic molecule. And out of this, if you look at this part, then it resembles parabolic potential. And if you suppose this to be the equilibrium bond length, then up to this distance plus x and up to this distance minus x, you can stretch the molecule and again bring back. This is really periodic motion. Beyond this, when you go beyond this distance, the molecule will break. When you go beyond this distance, the molecule will break. From here, this molecule starts breaking. There is no interaction. Okay, but up to this distance, for the timing, you could go above, slightly above this also. Okay, but up to this distance, certainly, if you allow, then it will be minus x to plus x distance. You can. So what does it means? It's a periodic motion which sets in. It means you can take the two molecules, a diatomic molecule, you can stretch it and you can compress it up to certain distance, stretching also and compressing also, and this vibration motion, vibrating motion sets into the diatomic into the chemical bond. This vibrating motion energy is actually V plus half h nu, where V could be 0, 1, 2, 3, 4, and this vibrating motion will give to the quantized energy level, and the moment you have quantized energy levels, then you can expose this system to the electromagnetic radiation, and the system can go from one energy level to another energy level, and you can get a spectra. So this study of simple harmonic oscillator is the basis of vibrational spectroscopy. So this is the basis of Okay. We will see later on that when we plot a graph of wave functions of the simple harmonic oscillator, it is also of the similar nature like we did earlier, but some difference will be there. Now the wave function will go to beyond the classical limit. Okay. For the second level, okay. So these are the points where the wave function is present, and the classical limit is that the particle should not go beyond the potential energy surface. This is the classical limit. In contrast to this, if you compare it with the particle in a one dimensional box, there what you were having, the wave function originated from x is equal to 0 and ended at x is equal to a. The boundary condition was that 0 to a. But here you observe that there is certain probability outside the classical limit also of particle being found. Okay. So all this we will do in details. We will do the calculations of these systems, and the purpose of saying you all these initial things are the results of the quantum mechanical calculation is that you should always keep it in mind that we are doing simple harmonic oscillator calculations since it is the basis for vibrational spectroscopy. Vibrational spectroscopy is also IR spectroscopy. Okay. So one thing is this one. Another is that why this simple harmonic oscillator, quantum mechanical simple harmonic oscillator, we are doing, because if we have to see the quantum mechanics in action, then it is spectroscopy. Okay. And in spectroscopy, this is meant for vibrational spectroscopy. When you do rotational spectroscopy, then that will be a microwave spectroscopy, that also we will be doing when we will do rigid rotor. Okay. But all this spectroscopy is the basis for the spectroscopy comes from the quantum mechanics. So in the next module, we will apply Schrodinger wave equation to this problem of simple harmonic oscillator, and we will try to find out a solution in a very simple way using the ladder operator, and then we will go for a little more complex calculation doing the power series method. Both these methods will give you the similar results, but the first one is a little simpler. So for the next module, in the next module we will again meet. Okay. Okay. So, the previous module I talked about the simple harmonic oscillators, its classical concepts, and what is the difference between classical simple harmonic oscillator and quantum simple harmonic oscillator we talked about. Now, we will try to find out, I have given you the results of the quantum mechanical calculation in the previous module, that what is the potential energy of a simple harmonic oscillator and what is the shape of a wave function which you obtain in the quantum mechanics. Okay. And now today we will be talking about, if we talk about simple harmonic motion, so today we will be talking about the simple harmonic quantum mechanical calculation on simple harmonic oscillator. Means we will apply Schrodinger wave equation to simple harmonic, bear with my handwriting because it is very sketchy, but whenever you sit to do this, to see these videos, you sit with a pen and paper and start doing it yourself, and you copy what I have done. Otherwise, simply looking at this video will not give you a clear concept. You will have to sit with a pen and paper and then do these calculations on your own, looking at this video wherever you feel problems. Okay. So, today we are doing, we are going to do simple harmonic oscillator, and we will be applying Schrodinger wave equation to this system. Since it is a one dimensional problem, so what you can write? You can write minus h cross square divided by 2m d square by dx square psi plus V is the Hamiltonian, apply it to the wave function, and what you get is E psi. So, H psi is equal to E psi, the Schrodinger wave equation. Okay. This potential energy we have seen is equal to 1 by 2 k x square or 1 by 2 m omega square x square. Okay. This we can write. So, if you put, for Schrodinger wave equation we can write minus h cross square divided by 2 m d square by dx square, okay, plus 1 by 2 m omega square x square psi is equal to E psi. This we can write. Can we express this Schrodinger wave equation in terms of x component of the momentum? You know the x component of the momentum Px has an operator h cross divided by I ddx. Okay. So, if you use this equation or minus I h cross ddx, both you can do. A square of this Px square will be, minus sign is already there, I square will be minus sign. So, it will be h cross square d square by dx square. So, if you compare this part with this equation, the only missing thing is 2m. So, let us do it. Px square divided by 2m becomes equal to h cross square divided by 2m d square by dx square. Okay. So, this part you can replace. You can replace Px square by 2m with this part. Okay. And then this whole part you can remove. So, what you get is Px square divided by 2m, and in order to bring this equation similar to the previous one, for the first term, we can change this term also, and we can write it 1 by 2m m square omega square x square into psi is equal to E psi, and now we can take out 1 by 2m outside, and so this will be equal to Px square. These are operators. Px square is an operator, and x square is also a position operator. So, m square omega square x square to psi is equal to E psi. This is very simple. Okay. So, your Schrodinger wave equation in terms of linear momentum becomes equal to this one, 1 by 2m Px square, an operator, m square is a constant mass, omega square is the angular frequency, and x is again position operator, x square into psi is equal to E psi. Okay. Now, if you use this equation, then so what you have? We have 1 by 2m Px square m omega x square into psi is equal to E psi. Now, this term within the bracket is, if you remember correctly, we have to factorize this term. Okay. If you remember, I said you that if you have x plus iy for z, then the complex conjugate you can write as x minus iy, so that z into z star becomes equal to x square plus y square. Can we do the same thing here? Can we factorize? Let us see it and do it and see what do you get. If we write at 1 by 2m and we factorize this term into, instead of Px, now I will be writing P only, Ip plus m omega x into minus Ip plus m omega x into psi is equal to E psi we can write. So, we have factorized this one, and what do you get? If you do the multiplication, Ip and minus Ip, minus sign is already there, I square will be minus, it will become plus, it will be P a square. Mind it, always remember that this P which I have written is a operator, x which I will write is an operator, it is not number. Okay, we are doing algebra of operators, so this should always be in your mind. And what is the difference between the two? In a number algebra and in a operator algebra, the difference is that the sequence matters. In case of number it does not matter, but in case of operators it does matters. Okay, sequence of operation is very important in operator algebra. So, this multiplied by this we did. Now, you multiply these two and what do you get? You get plus I m omega into P into x, okay, because P will come first, then x. Then you do the next one, multiply this with this one, plus minus minus I m omega and x into P, this you should get, okay. And then you multiply these two and these two will be m square omega square x square, psi is equal to E psi. Had it been number, you see I omega px and I m omega xp would go, but it is not number, so it will not go, okay. It will stay there because here you have px, this you always remember, here you have px and here you have xp, okay. So, this will not go, this will stay there, okay. Now, what I can write is minus a little rearrangement, nothing else. Or we can write if I write I m omega as common, then we can write x p minus p x, and what is this? This tells you, this is the definition of commutator. If you write commutator, in commutator we did, if you have A operator and B operator, then A operating on function like this one, and then again function like this one, this we say whatever you get is called commutator of A and B on the function this one. So, commutator is always written as within the bracket with a comma separated by two operators. So, this AB indicates AB minus BA, and BA will be BA minus AB. If I write commutator BA, it means BA minus AB. They may give the same result, they may not give the same result, means commutator may be 0, may not be 0. Okay. So, this is very important difference between number algebra and vector algebra, we talk operator algebra we talked about. Okay. So, this is xp minus px, and with this we can write as a commutator this will be commutator xp. Sorry, this is SI. There is SI. What is the value of this commutator? We did it earlier. Just to refresh you, xp and the px, what is the value? xp is I h cross and px is minus I h cross. Okay. So, if you use this, then what do you get? It is omega, and again I will have to go to the next page, 1 by 2 m p a square minus I m omega minus I m omega commutator of x p, then plus m square omega square x square m square omega square x square psi is equal to E psi, and xp commutator is I h cross. So, if you put I h cross, then I and I square will be minus, and then this will become plus 1 by 2 m p a square plus h cross m omega plus m square omega square x square psi is equal to E psi. This I can write. Okay. Now, having this, we will try to separate this into two parts. Okay. And we will okay. So, we have written it like this one. Now, we define two operators. In this format, I say A minus is m omega omega x plus I p x, and a plus is 1 by root under m omega minus I p x. If you compare these two, a minus and a plus, what you observe is that in the previous this point, at this point we already have these two equations, m omega x plus I p, m omega x minus I p, m omega x plus I p and m omega x minus I p. Only extra term is root under 1 by root under 2 h cross m omega, and this extra terms comes into picture because it has already been previously done, and it gives you the better results, nice looking results. So, this constant is introduced. Okay. So, this we can separate into the two equations, okay, and we can write, if we multiply it, if we use this equation, and now we try to find out a minus a plus, what it will be? It will be 1 by 2 h cross m omega x plus I p m omega x minus I p, and instead of this I write 2 h cross m omega, because it will be multiple of both a minus a plus. Okay. And again you do this whole exercise, what do you get? Finally, what you get is 1 by 2 h cross m omega p x square plus m square omega square x square on one part, then you get 1 by 2 h cross m omega, and the remaining part m omega x m omega h cross, because this already we have done it earlier, and we got here the same results. So, the same results I have copied in two parts. Okay. So, this is your a minus a plus. Okay. And this we can write, this is what, 1 by 2 h cross m omega p x square m square omega square x square. What is this? Now, you remember h Hamiltonian we have written as 1 over 2 m p x square plus m square omega square x square. So, this is your first term is actually the Hamiltonian, except you have 2 m is there, h omega is an extra term. So, what you can write? You can write a minus a plus is equal to 1, and 2 m is already there, h cross omega into Hamiltonian plus 1 by 2, and m omega h. So, omega and h cross will go, omega will go, h cross will also go, you will have 1 by 2 m, and this will be 1 by 2 m. So, what you can write is your a minus a plus becomes equal to 1 by 2 m and p x square 1 by 2 m, a minus a plus is so this part we have replaced 1 by h omega h cross plus 1 by 2 m. M should go, m should not remain here. M and m will also go. But m and m will also go. Why it should be here? Okay. So, m also goes. It is 1 by 2. Okay. So, a minus a plus is now 1 by 2, 1 by h. We can write now this as A minus A plus is equal to H Hamiltonian divided by H cross omega plus 1 by 2 plus 1 by 2. What does it mean? What is the Hamiltonian now? The Hamiltonian is now you multiply this H cross omega, then multiplied by A minus A plus, okay, and then you can take this on this side and it will be minus 1 by 2. Okay. Okay. Let me repeat this. It's a little cumbersome, so I am repeating. Okay. Now I am defining two operators. One operator is A minus, and which I will write as A minus operator, I will write as 1 by 2 root under 2 H cross m omega, then m omega x plus I p x. And another operator is A plus, which I will write as 1 by root under 2 H cross m omega x minus I p x. And the same thing we did in factorization also. Okay. So, if you find out A minus A plus, then you will be multiplying these two and the result will be 1 by 2 H cross m omega into m omega x plus I p x and then m omega x minus I p x. Okay. And this will give you 1 by 2 H cross m omega, multiply these two, what you get, m square omega square x square. Then you multiply this with this one, it will be minus I m omega x into p x. Then you multiply this with this one plus I m omega x into p x, and then you multiply these two, it will be minus, plus minus minus, and I square will be minus, so it will be plus p x square. You see the similar results which we have done earlier, we are getting here also. So, with this we can write as 2 H cross m omega, and this we can write as m square omega square x square, and then you take minus I m omega as common, it will be x into p x minus it will be p x into x. This will be, because you are multiplying this with this, it will be p x into x. Okay. So, it will be p x into x, okay, plus p x square. So, what do you get here? Again, this is equal to minus I h cross, this you know, this is equal to I h cross. So, I square will be there and minus will become plus, and you will have I. So, this you can write as 1 by 2 H cross m omega, and then you write p x square you bring it this side, then plus, this is plus sign, and I h cross will be I m omega h cross, and then plus m square omega square x square. If you separate them, if you separate them, then what you can write? You can write a minus a plus. Sorry. Now you can write a minus a plus is equal to 1 by 2 h cross m omega, and then I can write, I can take px square and m square omega square x square simultaneously, and I can write px square plus m square omega square x square in as one term, and another term we can write as 1 by 2 h cross m omega, and what remains there? What remains there is I m omega h. So, I m omega into h. I should also go, I think. Okay, this I will go because this is I h cross. So, I and I will get multiplied and I square will be minus 1. So, with a plus sign this I will go. So, we do not have this I you do not have, m omega h. Okay. So, m omega and h goes, you have 1 by 2, and this is what? This is nothing but 1 by 2. If you compare this with this one, you have this one 1 by 2 m is the Hamiltonian. Okay. So, this is Hamiltonian 1 by 2 m. So, 1 by h cross omega remains, and you have Hamiltonian here and plus 1 by 2. So, this you can write as a minus a plus minus 1 by 2 multiplied by h cross omega, and this is equal to Hamiltonian. Okay. So, the Hamiltonian of the Schrodinger wave equation in terms of the operator a minus and a plus becomes equal to h cross omega a minus a plus minus 1 by 2. Okay. In the same fashion, if you calculate a plus a minus, then you can write the Hamiltonian as, you can bring a Hamiltonian in the form of h cross omega a plus a minus plus 1 by 2. And if you find out the commutator for this Hamiltonian, means if you find out the commutator for a plus a minus, or then you get this equal to 1. Okay. A minus a plus, and if you find the commutator for this operator a minus a plus, this becomes equal to 1. So, you do this exercise, yourself, try to find out this operator, and do this exercise also, try to find out the yourself. Okay. Once you have this one, that a plus a minus so what we have, take home message is that Hamiltonian could be expressed in the form of ladder operator a minus and a plus into h cross omega, or Hamiltonian could be expressed as a plus a minus plus 1 by 2 h cross omega, and the commutator for this a minus a plus is equal to 1. Using this relationship, we can apply Schrodinger wave equation to a function and find out the next energy level, first energy level, second energy level, third energy. The first what we have done is h psi is equal to E psi, that we know. Okay. So, what will happen if we apply this commutator, these commutators to the ground state wave function? Okay. So, this we will try to find out in the next module. Okay. Thank you.